Here's an example using the quotient rule. So let's let f of x be this function e to the x over 1 plus x squared. Certainly this is a fraction of two functions. It's a quotient of two functions, so we ought to use the quotient rule. If we want to, in part A, find the derivative of f, and in part B, we want to find the equation of the tangent line to the curve f at the point where x is equal to 1. Okay, so again, we need to use the quotient rule, and then we should be able to find the answer to part B, no problem. So f of x is this quotient e to the x over 1 plus x squared. Our job is to find the derivative, so let's use the quotient rule. I'll call the top function a of x, and I'll call the bottom function b of x. So a of x is e to the x. That means a prime of x is also e to the x. If b of x is 1 plus x squared, then certainly b prime of x using the power rule is just 2 times x. And so according to the quotient rule, it's the derivative of the top times the bottom. So e to the x times 1 plus x squared, and then minus the top times the derivative of the bottom. So 2x times e to the x. So that's what we get in the numerator. And then we want to make sure that we divide by the bottom function squared. So 1 plus x squared quantity squared. So this would be a good final answer for part A. Find the derivative. We did that. Okay, so now in part B, we want to find the equation of the tangent line. So we need two things. If we want the equation of the tangent line at x equals 1, then we need f of 1 and we need f prime of 1. So certainly f of 1 is just plug a 1 in everywhere you see an x, so e to the 1 over 2. So I just get e over 2 for f of 1, and then f prime of 1, everywhere I see a 1, or sorry, everywhere I see an x, I'll write a 1. So I get e times 2 minus 2 times 1 times e. So that numerator just gives us 0. So that means the derivative is 0. And so now to remember to find the equation of the tangent line, it's f prime of 1 times x minus 1 plus f of 1. Well, f prime of 1 is 0, and then times x minus 1 plus e over 2. So this whole piece vanishes. And so the tangent line in this case is just a horizontal line, or the constant function L of x is equal to e over 2. So that would be a good final answer for part B. All right, our last example for the quotient rule is maybe an applied problem here. So the power capital P of a laptop computer is given by this formula. Capital P is equal to V squared R, capital R, over capital R plus little r quantity squared. So this is what the power of this laptop computer is. V is the voltage, capital R is the resistance, and lowercase r is something called internal resistance, whatever that means. So we want to find the derivative of the function P with respect to the variable capital R. So in this case, we can think of capital R as the moving variable, like the x in f of x, and then we can think of capital P as the y value, or the y in y equals f of x. So we want the derivative of capital P with respect to capital R. So we can treat all of the other letters, we will treat them like constants. The only moving part here is capital R, okay. And then we want to, we want to find the derivative of P with respect to capital R, and then for what value of capital R is the tangent line to the curve y equals P of R. So here you can think of P as a function of R, or P of R. When is that thing going to be horizontal? Here's a solution for part A. So our function here is capital P is equal to V squared big R over big R plus little r quantity squared. And so just to remind us that we think of capital P as a function of capital R, I'm going to write P of R, just like we would write y equals f of x to let us know that y is a function of the independent variable x. So again, I'm going to call the top function a of r, that's going to be v squared times big R, and I'll call the bottom function b of r big R plus little r quantity squared. And just so I can take the derivative, let me go ahead and FOIL this thing out. So big R squared plus 2 little r big R plus little r squared. Make sure you're good on how I got from here to here. And so now, the derivative of a of r, you can think of this thing as like 5 times x. So what's the derivative of 5x with respect to x? It's just 5. Or if the function was 6 times x and we want the derivative of 6x with respect to x, that's just the constant 6, right? So this is a linear function and the derivative is just the slope. So again, with respect to the variable r, this thing is a linear function and its derivative is just that number in front of the r. So the derivative of v squared big R with respect to big R is just v squared. And now the derivative of this thing with respect to big R, again, use the power rule. So that's 2 times big R, and then the number in front of the big R, so this is the linear part, so we just take 2 times little r, and then little r is a constant, and so the derivative of little r squared is just 0. So here is the derivative of b of r. So now we just assemble all the pieces using the quotient rule. It's the derivative of the top thing times the bottom thing minus the derivative of the bottom thing, so 2 times big R plus little r times the top thing. So this would be a good final answer for the derivative of p with respect to r. So for this one, we're looking for the value of capital R that makes the tangent line to the curve p is equal to p of r, I guess. When is that thing going to be horizontal? So horizontal tangent line means that the derivative is equal to 0. So the slope is equal to 0. So remember, we computed the derivative to be this thing, so we really need this fraction to be equal to 0. Remember that a fraction is equal to 0 if and only if the numerator is equal to 0. So in order to find where this fraction is 0, I just need to check where the numerator is equal to 0. So when is the numerator equal to 0? Well, let me factor out a v squared. And I can also factor out a big R plus little r. So when I do that, I get v squared, and then big R plus little r, and then what am I left with? Here I'm left with 1 big R plus little r, and then minus 2 times big R, right? Everything else we factored out. This thing in the parentheses can be reduced to little r minus big R. So when is this product equal to 0? It's 0 when one of the pieces is equal to 0. So this thing is 0 exactly when big R is equal to negative little r, and this thing is 0 exactly when big R is equal to little r. So that'll do it, right? When the resistance is equal to plus or minus the internal resistance, I'm not really sure how circuits work, but I don't know if you can have big R equal to negative little r, so you might want to rule out that option anyway. Okay, so this would be a good final answer for this problem.